So as I said, what we are talking about, what we had handled in the last class was a multivariable PD control. Okay, in which the multivariable part is that instead of taking, let us say, if you have a two-link manipulator, okay, so there are a torques tau1 acting in this joint and tau2 acting in this joint, and it will provide, it will cause some deflections Q1 and Q2. So in the independent joint control, what we had assumed is we had paired tau1 with Q1, tau2 with Q2, and any interaction, that is the effect of Q2 on the movement of Q1 or the effect of Q1 on the movement of Q2, that were considered as disturbances and basically ignored, and we had tried to compensate for disturbance by introducing a integral control action. Okay, but in case of multivariable control, you take them together. That is, you design tau1 and tau2 based on both Q1 and Q2. So you don't decouple both of them. You take the coupled equation, and because you are taking the coupled equation, it is quite possible that some of these terms which were initially considered as disturbances, they no longer need to be considered as disturbances. They can be handled more efficiently. Okay, and yeah, so that was the differentiation between the multivariable control and the independent joint control. Okay, and in the last class we had talked about multivariable PD controller. That is, your control U as such was Kp times the error in the joint variable minus Kd times the derivative of the time derivative of the joint variable or the joint velocity. Okay, so this Q tilde was a desired angle minus the actual desired joint variable Q, Qd, and the actual joint variable Q. Okay, now the problem here, or the what was not done here, is what was assumed is Qd was a constant, as the case was with the design of the ordinary PD controller as compared to the computer torque control. What we had done in the multivariable PD control was that the desired position was assumed to be constant, desired trajectory was not there. So in a more practical scenario, we would have Qd of t, that is, there is a trajectory that the joint has to follow, the joint position has to follow. Okay, and that was not taken into account in the PD part. So similar to the computer torque control, we will go for a control strategy that will incorporate, that will give the provision for having a varying reference position, varying reference Qd is possible now. However, the downside would be that this control will be more complicated, more complex, and as compared to the PD control case, as compared to the PD control case. And basically what we'll be doing is we will reverse engineer the control from the desired desired trajectory. So you have a desired trajectory, and from the desired trajectory, what you would say is that what will be the desired error profile that you want, and from that you will try to define what should be the acceleration that the joint has to follow, and from that you will see what is the torque. So that's the basic strategy. We will just try to, I'll elaborate as we progress into the lecture. Okay, so here this is the basic structure for a PD for the dynamics that describes the dynamics of an n-link manipulator, where this M, C, B, and G are, so M is a matrix, C is also a matrix, C, Q, Q dot will be a matrix. This B is the damping, G is the gravitational force, and U is the input that we are giving, and it depends upon the voltage. It has been modeled in a manner that this is proportional to the voltage that is supplied to the motor at each joint. Okay. Okay. Now in the inverse dynamics based control, as we said that we are trying to seek a feedback control of the form q dot, and it's a function of q dot and time, because all these three variables are measurable. That is, I can measure q from some optical sensors. Optical sensors can be used to sense the joint position. Tachometers can be used to sense the joint velocity. It's not very easy to measure joint acceleration. So we don't try to put any sensor in that. And of course, time may be measurable. We let us see that if we need to measure time explicitly. Okay. And the aim is to, when everything is solved together, what you should end up with is that you should have a linear closed loop system. So you have a nonlinear system. The actual system is nonlinear, and in the feedback also you put a nonlinear control. Okay, and maybe there is something here too. So, but effectively, when you solve all of them together, the reference to the position or the error dynamics. So QD minus Q, if you see what happens to that, the dynamics of QD minus Q, that should become linear. So that is the basic aim. Okay, so basically you want to cancel out all the non-linearities in the system. Okay, but there is one thing that we need to look into. Okay, so what we need to see is that, say you're tuning U. U is basically a voltage. This voltage is going to produce some torque, and that torque is directly going to influence the acceleration of the joint. So this torque is going to affect Q double dot. Okay, so basically, in order to cancel out the nonlinearity, we need to design a term that cancels out these highlighted. That this three terms need to be cancelled out first. Okay, so that's why initially what we are trying to do is, uh, first we assume, as in the case of the multivariable PD, we assume that the friction is negligible, and we ignore that part. And the next thing that is being done is to, since the joint angle and the joint velocity are measurable, we incorporate these terms CQ and G of Q into the control, so that the input basically shapes the acceleration of the joint variables. Let's see that if you add these two terms as in the control, what would happen? Okay, and then you say that you have a desired angular acceleration. Okay, so if U comes out to be this, then basically, let us say that you have a control structure of control of this structure, where the term highlighted in red is a control part that cancels out all the nonlinearities, and AQ is a desired acceleration profile. Okay, one thing is that this is not the desired acceleration. AQ is not equal to Q double dot. Okay, QD double dot. Okay, can you say why that is? If you have, I'll give you one. Okay, so I'll give an answer to that too. Okay, so what we have is, you have QD as some desired trajectory. So you also have QD dot, you also have QD double dot. Okay, now if we assume that AQ, that is the desired acceleration profile that you want, or the acceleration that you want the joint to follow, if you assume this to be QD double dot, the acceleration, and if you say that there is an initial error, that is Q of 0, the joint position at the start of your control cycle is not equal to QD0. Let's say if this happens, then the trajectories will deviate. Okay, but you want the trajectories to converge. Even if you say, even leave out the acceleration part. Even if you assume that your the desired Q dot is equal to QD dot, even this assumption would turn out to be wrong, because then what you are asking is that both the joint should move at the same speed at the desired this thing. So you have QD dot like the QD to be moving at this rate, and you also want Q to be moving at this rate. So what you have is you are maintaining a constant error. You are not maintaining an error that converges to 0. So that's the basic takeaway that basic point that I want to say is that AQ is not actually QD double dot. AQ should be something that should be designed based on these entire information about the desired profile, desired trajectory, and information about what is the actual joint position and the joint angle. Okay. So basically what you want is you want Q double dot to be AQ. You really don't want Q double dot is equal to QD double dot is not the aim. Okay, but if you have Q double dot is AQ, then the desired acceleration and actual acceleration should have a linear relationship. And since you want a linear relationship overall, AQ should be some linear function of your errors also. Okay, let's say, so since we are talking about error, let's define the error as Q minus QD. Okay, and you want a control such that this error converges, it becomes stable. Okay, so let's have this desired dynamics of the error. Okay, where KV and KP are positive definite diagonal matrices. Okay, so we are saying diagonal matrices for simplicity, but even if they are positive definite matrix, I think it should work out. But let's stick to diagonal matrix for simplicity. Okay, so you have KP and KV to be diagonal matrices which are positive definite, and this is your dynamics. Now what does this mean? It means that if you substitute this, okay, and if you say that if this has to be desired, then what you're basically saying is Q double dot minus QD double dot, but Q double dot was AQ. Okay, so you have AQ minus QD double dot plus KV into Q dot minus QD dot plus KP into Q minus QD. This should be equal to 0. Okay, so if rewriting this, you get this equation. Okay, which says AQ is Q double dot, which is dependent upon all the acceleration of your reference and the velocity and position of the desired velocity and actual velocity, desired position and actual position. Okay. Okay, so this should not be K0, K1. This should be KD and KP. I have to make that corrections. Okay, so let's say that as I said that a simple choice for KP and KB, that one of the choices, say this is one choice that we can design is use KP, choose some frequencies omega 1 to omega n and assign KP is omega 1 square to omega n square in a diagonal format, and KP is twice omega 1. And then this equation will turn out to be a matrix equation which has this structure. Okay, which has this structure. Now you see that in each of these terms, okay, each of these, this is a set of n equations, and in this n equation there is no n equations, there is no cross coupling. E1 double dots equation doesn't involve any of these derivative or any of these uh, joint errors also. So you basically have an equation with one variable for I is equal to 1 to n. Okay, now since this has been chosen such that this is the term associated with E dot is 2 omega 1 and the term associated with E is omega square, what you have here is a system where you have the damping ratio to be equal to 1. You have a system that is critically damped. Okay, so this you will have a system that is critically damped, which is what is the ideal situation in case of a robotic manipulator. You want critical damping in a robotic manipulator, and with a natural frequency, a chosen natural frequency of omega I. Okay, so even if you're not able to exactly nail kV to be 2 omega, you may able to get it very close to 2 omega. So your the close to performance will be very close to the ideal case of a critically damped system. Yeah. So what you have is that the effective torque is mq, m of q into a of q, which we have calculated here, plus these two terms. Okay. Now the advantage is that you are able to track any arbitrary reference signal. However, the disadvantage that you have is that you need online computation of all these matrices. You need to compute these three terms online at every instant of time. At every sampling instant, this needs to be computed. And that is why this becomes more complicated than the computed torque control, where you did not compute these terms online. Okay, you had computed C of QD dot. Okay, you had computed terms like this, which looked nonlinear, but actually they didn't involve any online computation. Okay, so in this case, you require online computation because you want C of Q comma Q dot, not QD comma QD dot. Okay, and because of that, you may need a signal processing based controller that does all this work. Okay, so basically in this case, you have an outer loop and an inner loop. Okay, the outer loop will be a nonlinear control. Sorry, the outer loop will be a linear control and the inner loop would be a nonlinear control. Okay, so the inner loop is that C Q comma Q dot. The inner loop uses these terms and it uses the DSP process, and the outer loop just shapes the acceleration AQ based on the measurement of your reference and the actual joint angles. Okay, and so as we said that the computation of the inner loop will be a nonlinear one. Okay, and the outer loop is error driven feedback for the system, and the outer loop, which was the inner loop, will be made into a linear system. After the implementation of the inner loop, this system that the outer loop sees will be a linear system. Okay, now until now what we have been doing is that we are doing all this computation, all this references were given in terms of the joint space, in terms of QD. However, what you actually have in a practical situation is you would be given the positions and the angles. Maybe you will be given the Euler angle notation for the joint orientation for the end effector probably, and you may be given the end effector position. So if you have an n-link manipulator, let us say if you have a 3-link manipulator or a 2-link manipulator with an end effector, the specification is not really given in what this joint is and in what this joint is. What would be given is what is the effective position of this end effector and probably what will be its orientation. Okay, so you need to translate that in terms of the joints. Okay, so you have the homogeneous transformation to get from q to theta, means q to xy theta. Okay, and we can actually modify the outer loop without changing the inner loop and translate our control that we had done in the joint space to the task space. Okay, so if you would remember that in the kinematics part of the task space, you have a Jacobian matrix J that relates the velocities in the joint space with the velocities in the task space or the coordinate space. I mean, say in the task space, the workspace, that is, you can say X is the workspace coordinate or the task space coordinate. Okay, so X dot is related to Q dot with this relationship J of Q into Q dot. And X double dot is simply J of Q into Q double dot. It's just the derivative of this expression. Okay, and now if you choose, so from this, since Q double dot is actually AQ as for the control purpose, if you choose AQ, if you design AQ to be J inverse this expression, where you have AX you define as the desired acceleration in task space. Okay, that is X double dot is AX. That is what we want to get in. Then you can reverse engineer, or you can express the same outer loop control. You can modify the outer loop control to be based on the error in the task space rather than the error in the joint space. So instead of QD, you will have XD, and you can use a gains that have a similar structure. KP and KD may have the similar structure. However, the errors in the position and velocities are now being measured in terms in the task space or the Cartesian space. Okay, and if you solve this equation, you would again get a linear equation in the error in the task space. Okay, and now with this alone, the inner loop need not be checked. The inner loop is still a control that is based on your joints and joint angles, but the outer loop is now based on the task space dynamics. So you have a task based control here, and in the inner loop, you have a joint based control. So there is a loop here and there is another loop here. Okay. The earlier notation that we had talked about was in terms of a generalized coordinate, a minimal representation in task space. However, it's more common to have the representation of your position and orientation of the end effector using Cartesian coordinates x, y, z and the Euler angle phi theta psi. So in that case, this generalized xd d trajectory, okay, generalized this thing, the task space coordinates, simplifies to something that is more relatable as the position d and the orientation theta phi psi. Okay, and d dot will be velocity, and the derivative of your joint angles, not joint angles, the derivative of your Euler angles is the angular velocity omega. 3-dimensional angular velocity omega, and then you can have the acceleration also defined in the same coordinates. Okay. Okay. So in conclusion, what you have is that now if you are doing your when you are doing your control design in the joint space, there is no ambiguity of how the joint should move, because the torque is directly affecting the acceleration of the joint. Okay, there is no ambiguity in the how the joint is, will move if you give the specification in terms of the joint itself. However, when you're doing your when you're giving your specification in the task space, it becomes more unclear, because now there is an additional condition that whatever trajectory that is being given xd in the task space should be possible. Okay, so let's let's say one thing. Let me clarify that using an example. Let's say that you have a link L1 and you have a link L2. Okay, and I say, and let us say this is Q1 and Q2. Okay, so any trajectory QD1 and QD2, okay, where the positions are like where it is this QD1 goes from 0 to 2 pi and QD2 goes from 0 to 2 pi is valid, and I would have I just need to get Q to QD and the problem is solved now. Okay, however, let us take the same joint. Let's say this link is L1, this is link is L2, and let us say that I want to go to a point. So let's say that these trajectories are X and Y, and I give the specification that I want to reach L1 plus L2 plus 1, comma 0, this position. But even if I have both the joints aligned along the X direction, the maximum length it can go, the maximum length this end effector point can go is only L1 plus L2. So this position is not really reachable. Okay, so it should, so in while you are doing your specification in terms of task space dynamics, then you should be sure that it should be possible. Okay, and we had done something, we had seen something that we are doing this inverse of the Jacobian matrix. Now, the Jacobian matrix relates the joint variables, the joint velocities to the velocities in the task space. Okay, so it is a matrix that may be square, that may be fat, or that may be tall. Okay, so that would mean that when I'm trying to find the inverse, okay, the inverse should actually exist. You see, I should be able to go from your from the given specification in the task space to a specification, to an equivalent specification in the joint space. That should be possible. So J inverse Q should be computable even if I'm using techniques of a pseudo inverse. Okay. So basically what we are talking about is the Jacobian should be non-singular, and the point that we are talking about with the task space specification that are given should be reachable. The task space point, the maneuver that we are talking about, that should be reachable. Now this is as far as the control using inverse dynamics is control. But until now, what we have thought about, even in the nonlinear control, the seemingly nonlinear controls of computer torque control and the inverse dynamics based control, what we had assumed is that we have the perfect knowledge of the model parameters. And no, we don't cater to variation of the parameters, because it may happen that let us say if there is a robot that is a pick and place robot. So you have the end effector here. It goes to some position. It has to pick some object and go to some other position. This can be specified, but after it picks up an object, then the weight of this joint has changed now. So the control strategies that we are talking and we have talked until now, they don't take this into account. And they assume first thing that they assume that the parameters are known and the parameters are constant. So, but practically you can't be very sure, you can't be 100% sure about the values of all the parameters. So you need a controller that is robust. Okay, a robust controller can handle variations parameters while delivering satisfactory performance. May not be the optimal performance, but the performance would be satisfactory enough. And adaptive control, on the other hand, changes the means it doesn't assume prior knowledge of the model parameters, and the controller gains, let us say if it is a PD controller, KP and KD gains are tuned to best suit the problem at hand. So KP and KD are not constants when you're talking about an adaptive controller. You'll not go into design of the robust or adaptive controller. I'm just specifying what other choices of control are present here. So there are a number of robust and adaptive controllers approaches that are available for the control of robotic manipulators. Few are listed here. You can refer to additional text for further information. You can even refer to the textbook that I have specified. Okay, so one is robust feedback linearization, where similar to the inverse dynamics, but you assume less amount about the knowledge of the parameters. In inverse dynamics, you had assumed that you have perfect knowledge about the system parameters. Here you assume less. Instead of saying m of q, you use an estimate of m of q. Okay. Similarly, instead of having c of q comma q dot, you have an estimate of c of q comma q dot in your control. And using that estimate, using a nominal value, you try to tune the outer loop control so that your system becomes stable. Okay, and Lyapunov approach is used to estimate to ascertain the stability. Okay, and you also have something called as a passivity-based robust and adaptive control. In a passivity-based control, basically you assume that every system has some amount of friction. Okay, so if I tune in a manner that the energy is minimized, the friction term is tuned in a manner that the energy is minimized when the error tends to 0, then you have passivity-based control. Okay, so that is it based on the philosophy that every system is has decidedly passive aerodynamics and will decay to 0 or minimal error eventually. So the error that the dynamics is tuned in a manner such that the 0 point is the point when the error is 0. Okay, and in the case of an adaptive control, you represent the nonlinearity as a set of parameters which have to be estimated. So use an estimator to continuously use your measurements of the q and q dot to again estimate what the parameters are, then to tune. So from q and q dot, you estimate your masks and the Coriolis matrix. From this, you find what is the best suited values of Kp, Kd, etc. for that system. Okay, and as I said that in more detailed knowledge of these control strategies, you can refer to additional text. So with this, we come to end of this particular lecture. Okay, thank you for that.